Well, the thing about evolution is it's not directed. We can't really make predictions about what's going to happen in the future. All we can do is look at what's there now and make guesses as to how we arrived at that situation. So I think our general thinking with Ceratomyxus shasta, and indeed many other parasites and viruses, is that you would have started with a common ancestor that would have probably come in a salmon from the ocean. Most of these Ceratomyxes are out in the ocean now. There's very, very, very few in fresh water. In that sense, Ceratomyxus shasta is almost unique in that it's one of the few freshwater species of this group, the Ceratomyxa. So we would have had a common ancestor probably come in via a salmon from the ocean. It got lucky. It found itself that there was also a freshwater polychaete host. And just like Ceratomyxes, the freshwater polychaetes are very rare. There aren't many species of freshwater polychaetes. So this ancestor parasite got lucky. It had its two hosts there, the salmon that were always coming in. It found a freshwater polychaete. And if we had genotyped it then, we would have found that there was only one genotype. But what has happened over time, because we've got all of these different salmonids that go about, they go back to the same stream they spawned in. We've got different species of salmonids that spawn at different times of the year. All of these different host behaviours separate the parasite in time and space, and that gives evolution the tools it needs to work. We see that there would always be this random background level of mutations in the 18S gene, for example. But if all the fish and parasites are staying in the one area, these changes tend to not amount to anything. They even out over time. And so what happens over time is when you have a separation of parasites in time and space, we get an interruption into what's called into gene flow. If a parasite population is all in the one place with its host, we speak of that as being a fairly high gene flow situation. There's a lot of mixing between the life stages and the hosts. But as soon as you start to say that, well, the Chinook salmon only come in summer and the coho come in winter, you get this spatial and time separation in the hosts. And these natural mutations that are occurring all the time get a chance to build up. And you get to a point where if you then go and genotype parasites from different hosts, you see, oh, hang on, this one's a little bit different. In terms of sort of any optimization that occurs between a parasite and its host, I think that again is a process that will take time. And in some ways you could argue that Ceratomyxus shasta isn't there because it's getting into some of these populations and decimating them, these highly susceptible rainbow trout. That isn't a sustainable life plan for these parasites. They don't want to, your parasite doesn't want to do that, because if it gets in there and it kills 100% of its host this season, there's no host for it to infect next season and the parasite will die out along with the host. In a lot of ways, parasitologists talk in terms of an ideal parasite, and the ideal parasite is not one that kills its host. I mean, contrary to many science fiction movies where people are dying in horrible bloody ways, sorry, diversion, the ideal parasite is one that doesn't kill its host. All it needs to do to sustain its own life cycle is to enter its host, undergo development, produce spores. If that doesn't kill the host, that's great. The host remains healthy. It's swimming around the river, spreading spores into new locations. It doesn't need to die for the parasite life cycle to be sustained. So I think more the situation we see in these red band trout and the native steelhead, where you have a low level of mortality, the parasite's there, it's fairly prevalent, but it's not killing the host. I think that's a better example of where it's had time to co-evolve with the host. If we think back to the ancestral situation where the Klamath was a free river and these fish were roaming over large distances, we probably would have expected to see a lot more mixing of the parasite population, and perhaps there weren't as many genotypes because you're getting this high gene flow. The parasites and the hosts are all mixing. But as soon as you introduce a barrier to this gene flow, in the case of the Klamath River, we have barriers put in by man. We have dams put in that have separated lower river populations of anadromous fish from upper river populations of these resident rainbow trout. What we see then is that can drive parasite evolution, in that we've separated the populations of hosts, we've separated the populations of parasites, and we could expect over time to see development of new strains of the parasite. Well, I think quite clearly there is a separation to upper and lower basin in terms of the parasite strains. We've seen type 1 only in the lower basin in the Chinook, and I think that is a direct example of we've put the dam in, the Chinook can't get past, they're not bringing their genotype into the upper basin anymore. There's no more type 1 in the upper basin. You could imagine that final season where the dam went in, there were no more Chinook coming up, the type 1 that was living in or overwintering in the polychaete populations would have been spat out into the water as actinospores, and there would have been no hosts, and so the life cycle was stopped. The other situation with the resident rainbow trout, for example, the red band rainbow trout, we've only seen type 0 in them, but we've seen type 0 in both the upper and lower basin. And I think that's an example where that genotype wasn't affected by the dams so much because we haven't got migratory fish. They might be migrating from the tributaries down into the lakes to spawn, but because they're not migrating where the dams have blocked them, the parasite has been able to sustain. I think 100 years isn't very long in the scheme of things. And I think where we've seen the elimination of type 1 from the upper basin when we eliminated the Chinook, I think that's a very direct, immediate result of the dams. I think if we want to talk about the type 0 that's above the dam versus the type 0 that's below the dam, I think we might need a lot longer in time to see drift of those populations apart to where we can detect them using the methods we're using now. It's quite possible that we could look at other genes and see that there is a difference in the two populations, but not in the 18S or the ITS.